All right, we're going to continue with chemistry, even though I am hopefully, Lord willing, in the Caribbean and enjoying 88-degree weather, although 60 sounds better to me than 88, but hopefully we are serving the Lord faithfully there. As we move on, you're probably going to want a piece of paper and a pen or pencil, and you'll need a calculator. The first part as we go through this next step in stoichiometry, you don't have to write down the simple stuff. I think you'll know how to do that, but it's the same thing that you will use when we get to the chemistry part. But the chemistry examples I'd have you write down, because then you can look back and look at how we did these, and you should be able to answer the questions that are assigned to you. So this is still stoichiometry, and spring break, so it has gone to sleep. It is just stoichiometry 2.0. Now it's limiting reactants, and it's going to seem a little bit trickier when you start out, but it's really the same thing. You just have one more step at the beginning, and it's not even that difficult, but it's easy to forget one of the steps. So you have to be careful, be patient, choose wisely how you proceed as we go through. If you don't follow along because you think, well, he's not here, he's not going to grade anything right away, it will happen, and there will be, right after I get back, there will be quizzes, and this is pretty much the end of this section, so there will be a test or an assessment activity at the end of this. And if you think that, oh, just before you're going to pick this all up, then as it says, you will be hit like a Kenny Bell block if you don't happen to remember Kenny Bell and his famous block. All right, we don't want that to happen, so out of my desire for you to do well, you will need paper to copy the examples when we get to the chemistry part, and you will need a calculator. It's one of those things that will seem really simple if you just watch me do it or if you watch somebody else, and then you'll be really confused and think that the questions are completely different when it's actually you that has to do them. So follow along, and we're going to start out really simple, and then it will build up to where we're going to be, which is still not real difficult. Remember, it's only one extra step to the stoichiometry you're already comfortable with and know and love. Okay, so what is a limiting reactant? Limiting reactant is the reactant that will be used up first and stop the reaction. This is the reaction we did. We did in a test tube. This is a picture of it being done in a beaker, a little larger scale. The copper wire put into a clear aqueous solution of silver nitrate, and the silver part precipitates out and becomes a solid here, and the copper goes into solution, and that's why you see the copper nitrate has that bluish tinge. Here is the equation. As we look through, and these are the two reactants, and there's still lots of copper. We can see copper here, and this is still in a coil form. It would not be that silver. The little crystals are so delicate and tiny. If you took the coil right out of there, it would all just become a lump on the bottom. So the fact it's still in the coil form shows that there's still copper there. There's lots of copper to react. We ran out of the silver nitrate. They ran out of the silver nitrate. We did too, because the silver nitrate is, of course, the expensive part of this. So we have a fairly dilute amount of silver nitrate in there. And once the silver has all been used up out of there, and we've gotten all the silver out of the silver nitrate, the reaction stops. Still lots of copper left, but we're ran out of silver nitrate, so the silver nitrate was the limiting reactant, and now the reaction has stopped. A very simple example, except if you could do this one, then you will understand all of the examples we're going to do. They're just not worded as this, and it's nice when things come together in 1-to-1 ratios. They don't always come together in 1-to-1 ratio. It's easier to picture then. You have 75 right-hand gloves and 45 left-hand gloves. What is going to be the limiting reactant? Which one, as you're making pairs, which one are you going to run out of first? As you start making a pair from each pair, we're going to run out. We have less of these, so we have fewer. We're going to run out of the left-hand gloves first. That will be our limiting reactant. And after that, you can't make any more pairs. How many pairs will we have made? Well, it's dependent on the left-hand gloves, and we need one for every one of them, so for every pair, so we can only make 45. See, I told you this was simple. Nobody would have had any problem with this. How many gloves and what kind are left over? Well, if we've used up all the left-hand gloves, it's going to be the right-hand gloves. And to use up, when we use 45 of these, that will take 45 of those. We have 30 left over, so we will have 30 right-hand gloves left over after the reaction has stopped. In this case, after the process has stopped of making pairs. This is where I would ask if you have any questions, but I'm going to assume that you don't since I can't hear you. Example 2, this is one that Mrs. Lovegren would use. A recipe calls for 2 eggs and 3½ cups of flour to make a batch of cookies. Now we're going to talk about all the other ingredients. We're going to say we have an excess of all the other ingredients. You can't really make cookies out of just eggs and flour. That would be more like baked paste or glue of some kind. But we've got all of the butter and the sugar and the chocolate chips, whatever you want to make your cookies out of. But we're worried about which we're going to run out of first, the flour or the eggs. So each batch needs 2 eggs and 3½ cups of flour. You have 12 eggs, you got a full dozen, and 17½ cups of flour. What is the limiting reactant and how many batches can you make? So we're going to do this the same way when we get to the chemistry part, which is the next slide. We're going to actually write them out, because a lot of times people do math and then when they're done, they have no idea which math goes which reactant, and they still get the answer wrong even though the math is done properly. So I'm going to have eggs and I'm going to have flour. And I have 12 eggs and I need 2 eggs per batch. And I have 17½ cups of flour, and I need 3½ cups per batch. We do the math, and hopefully we don't need the calculators yet. 12 divided by 2, we can make 6 batches. With this, 17.5 divided by 3.5 is 5 batches. So since we can make 6 with this, but only 5 with this, we're going to run out after 5 batches of cookies, we're going to run out of, then flour is going to be our limiting reactant. That's the one we're going to run out of first. And since we have 5 batches, to do 5 batches, each one takes 2 eggs. That would take 10 eggs. We would have 2 eggs that would be left over. So we could make 5 batches of cookies and you'd have 2 eggs left when you were finished. Now if you can do this, then all the rest of it is going to be exactly the same. And you can pause the video anytime you want to rewind if you need to hear something again, but hopefully that was clear. Okay, the first one that we're going to do with a chemical reaction, we'll use this reaction a couple of times. Simple. We take hydrogen and react it with oxygen and we get water. So how much water can be made from 15 grams of hydrogen and 45 grams of oxygen? Well, I'm going to do the same thing. I'm going to put down the hydrogen and the oxygen so I know exactly what I'm dealing with. And I have 15 grams. And when I go across and do stoichiometry, I can't do it in mass. I can do it in moles, though, so I'm going to turn this into moles. And we can use the formulas over there. And 15 grams divided by the molecular weight of hydrogen, 2.016 grams per mole. And oxygen, I have 45 grams divided by O2 is 32 grams per mole. Remember that since these are diatomic, they're part of the Magnificent Seven, that we have to use the molecular weight, not the atomic. So it's not 1.008 or 1.01 if you're using the copied sheet, and not 16, but it'll be 13. It's going to be doubled those. And if I run those numbers quick, I get 7.4405. That's way more than I need. 45 divided by 32, 1.4063. All right, that's how many moles that I have of each. Now when I look at the equation, it takes 2 moles for every 1 mole of oxygen. So I have to take the coefficient here, and I'm going to divide this, the number of moles, by how many moles we need per reaction, per batch, like we did in the cookies. So if I take the 7.4405 divided by 2, I get 3.7. This is 1. So if I divide it by 1, I still have that amount. So this would be, I could make 1.4 reactions. This one, 3.7. So my oxygen is going to be my limiting reactant, even though I need 2 moles for every one of the reactions as we go across. And then the stoichiometry is exactly what we've done before. All of this we did just to say that we're going to pick this one. And so this part, unless there's a second part to the question, we aren't going to need now. And the question is just like what you could have answered earlier in the chapter, how much water can be made from 45 grams of oxygen? We just needed to know which one of them we're going to use. So now we're going to start with, you could start over from here again, but we've already turned it into moles. So we can turn it into moles, 1.406 moles times 2 over 1, desired over given, times the molecular weight of water, which as nerds, we now know is 18.016. And that equals to two significant digits, 51 grams of water. So we found the number of moles of each one, and then we took and divided them by the coefficients that are here, and there is no 1 here, so it's an assumed 1. And when we divide this by 2, we get 3.7. That's still larger than the 1.4, so this becomes our limiting reactant. We just take this number of moles, and it goes into our stoichiometry problem. Remember to write it out in this way so that in case you got mixed up and you flipped the 2 and the 1, that you would still get partial credit. All right, hopefully that made sense. Now I have one that I'm going to have you do on your own. 2Na plus Cl2 will produce 2 NaCl. Hopefully you can read that on the screen. Just in case, I will write it larger. 2Na plus Cl2 will produce 2 NaCl is your balanced equation. And how many grams of sodium? So this will become our desired, our two givens. We have 150 grams of sodium, and we have 300 grams of chlorine. Go ahead and figure out which is the limiting reactant, and then do the stoichiometry. And while you can do that, I will provide you with a little calypso or Caribbean music to stimulate your thinking. That music, although it sounds like it was made by a synthesizer, is actually made by drums, steel drums that were originated in Trinidad, and they made them out of the oil drums that they had laying around everywhere. They would take and beat them until the different parts that they made on them rang a different tune, but it sounds like a synthesizer, but it's actually a steel drum. All right. So we got to figure out which one of these is going to be the limiting reactant. So if you take the sodium and you take 150 grams divided by its atomic weight, we get 6.5246 moles. The chlorine divided by its weight, remember it's diatomic, so we have to multiply the 35.45 times 2, so you get 70.9, and we get 4.23 moles. But we still have to figure out how many reactions, how many batches of NaCl can we make. And since they come in the same 2-to-1 ratio with this, since it has 2, we're going to take and we're going to move that 2 down, and we have to divide that by 2. And the 1 you don't really have to, but we take the 1 down and we divide it by 1. I would hope that you don't actually put that into your calculator, but I guess I won't be too disturbed if you actually do. When you do this one, it comes out to 3.3. Now I don't care about how many significant digits are here because I'm not going to use this number. This is just going to be compared to this, and 4.2 divided by 1 is still 4.2. So in this case, 3.3 is now less than 4.2, so I'm going to use the 3.3 to write my equation. So I will use the regular stoichiometry, and again, I've gone through just to eliminate this whole part of it is now gone. So the question ends there. How many grams of sodium chloride can be produced from 150 grams of sodium? The other is interesting, but we're going to use up some of it, but we're going to have some left over there. And theoretically, we're going to use up all of the sodium. You never quite do, and so there's the theoretical yield and the actual yield. For right now, we're just worried about the theoretical yield, what we could get. So if we put that in, we're going to take, remember, we don't use the 3.3. We have to go back to the moles. So the moles go down here times 2 over 2, desired over given. If I move this out of the way, you can see desired over given, 2 over 2. Even though it's 1, you know it's 1, put it in there in case you need the partial credit, times the molecular weight of sodium chloride, 58.44 to 2 significant digits, comes out to be approximately 380 grams of sodium chloride. All right, and hopefully that makes sense. If you need to take a picture of the board, or if you didn't write it all down, I suppose that would be all right if they pause the video, but hopefully you were able to keep up with that. Okay, one more for you to do on your own. Back to the hydrogen and oxygen, and hopefully I can get some hydrogen. We can actually do this reaction a couple of different ways. It's kind of interesting. So it says how many grams of water can be formed by reacting 35 moles of hydrogen with 25 moles of oxygen. Students think that these all of a sudden it's harder now because it's in moles, it's not in grams. I'm used to grams. This question has started you one step ahead. The first thing we did in the last one is we had to turn it into moles. But now they've done that for us. They've already given us the moles. So it's not harder, it's actually easier, but you have to be careful that you don't just continue doing the same thing and take the 35 divided by the 2.016 because it's already in moles. So you've already got moles there. You still have to figure out which one you're going to run out of first and then do the stoichiometry. So go ahead. Work on that for a moment or two. So if we start with the same thing, we already have the moles, so we divide them by, things in the way again, 2 molecules of hydrogen for every 1 molecule of oxygen, so we're going to divide this by 2, and so 35 divided by 2 is 17 and a half. 25 divided by 1 is still just 25. This one is going to be my limiting reactant. So I'm going to write the stoichiometry using hydrogen. But again, remember, this is important for comparing to that, but I don't use it. I'm going to go back to the number of moles. So 35, the number of moles, times 2 over 2 again, desired over given, times the molecular weight of water, which we are familiar with at this point, will give us approximately, to 2 significant digits, 630 grams of water. All right, and that's the type of questions that you're going to have. The only thing that's new is this part here, eliminating which one are you going to actually use. Once you've chosen that, then make sure you go back to the number of moles, not the number of reactions that you have, the number of moles. Now, in a lot of places, if you get confused, this isn't covered in your textbook this year. They don't do a very good job of that, but if you go online, a lot of times the way that they recommend you do it is, and sometimes you can have 3 or even 4 reactants that you're going through, and their idea is just go through and do the stoichiometry for each one, and then just pick the one that gives you the least amount, which I think this shortcuts that, and you can pick the one and you only have to do stoichiometry once, and I think this one makes more sense, at least to me. But if you want to just go through and write the stoichiometry for the 35 moles and for the 25 moles and see what you get, if you did it for the 25 moles, you would actually come up with more grams of water than that. Always choose the smallest one. You will now get a sheet that has practice on it and a few questions, and there will be a key put out so you can make sure you're on the right track. And use peer tutoring if you understand and somebody beside you doesn't. Don't just give them the answers. That doesn't help them at all. Make sure that you are sharing why you did it. If you aren't sure, ask questions exactly where it is that you have lost the connection there, and ask, well, why did you do this? Where did you get this number from? And they can explain it to you. Probably the easiest way to get good at this is trying to teach somebody else how to do it. So use that as a tool to improve your skills and to be the good Samaritan. And if somebody shows you something, then be quick to show something to somebody else as well. After you're done with that and you've checked that, then there will be, after we're done with the practice, then it will be game time. There will be another sheet that you will fill out. This one does have your name on it, and it will be turned in for credit. That's why the first one is not, and it has the key that's put out. If you get stuck on the second one, then look back at the first one and see what did we do, and you can look at mine, see what did I do on that one. And then there will be one more sheet after that. Neither of them have very many questions on them, so it shouldn't be too arduous, but again, make sure that you keep up, don't get behind and then think you're going to catch up just before the test. Thanks, and have fun.